Okay, so we're talking a little bit about trusses again. Do you remember there was a difference between trusses and frames? What did trusses only have?
External?
Anything could be internal or external, right? Depending on whether you cut it or not. If you cut it, it becomes external. If you don't cut it, it's internal, right? Right now on your elbow, there are internal forces. If Eugene broke your forearm, then we could analyze your elbow for external loads, right?
Okay.
Okay. So what's the thing that's different between trusses and frames? Trusses only have two force members. And what's a two force member? It's a member that only has the forces and the connections at the end. Once it has a force or a connection inside, it becomes a three-force member, and then we're dealing with frames. So frames can have two forces, but if you have if all the members are two-force members, it is a truss. If you only have two force members, it's a truss. Now, remember when we looked at trusses, some of the members were zero-force members, right? Do you remember those two rules? So I want you to get a reminder of those two rules. So what was rule 1? If you have two members that come together at a joint, and at that joint there is, thank you, you have two members come together, only two, at a joint, and at that joint we have no external loads or a main support. What does it tell us? These two are zero force members.
Yes.
Okay, what's rule 2?
Perpendicular.
If there is
Two that are collinear and one non-collinear at a joint. No external forces or supports, and what's 0? This one is 0. Okay, so I know we did some practice, but I want to look at, let's look at this one first. Jack, which joint, Jack, is there a rule 1?
No.
Why not?
There's not two members coming together at one point with no external force.
Right, so the place where the two, joint A and joint E, have two members coming together, but there's an external support. Is there a rule 2? Nicholas?
Yeah.
Nicholas? Which joint makes rule 2?
BC? No.
Which joint makes rule 2? You're always looking at a joint.
B?
Joint B. There's two are collinear, one non-collinear. Which one's 0?
BG?
BG is 0. Nick, is there another rule 2?
Yeah, joint D.
Joint D, and what's 0?
The DF.
Yeah. Okay, now we're going to go down to this one. This is the one that's interesting. Chelsea gets this one. No, I guess not. Chelsea, is there a rule 1?
No.
No. Ah, you got one. Rachel, is there a rule 2? Which joint is rule 2? It's not hard yet, it's going to land on Sarah. Which joint is rule 2?
There's only one that goes. Well, I don't see one.
Rule 2 is where there's a joint where two are collinear and one's non-collinear. And look at the one I'm circling. Oh, you were looking at the wrong one. This is the one we're doing.
No, that's the one I was looking at.
Oh,
I just see 2 are connected to the collinear one.
okay. But what joint were you looking at?
E and D.
Okay, so look harder. Let's give her a hint. On the bottom.
Oh, okay.
Okay, so which joint?
It's FD is 0 and H.
Right, so joint F, and DEF is 0. and H, right? And BH is 0. There is another rule too. No, you have to look at the joint. Don't let anything else. Don't get your, don't, you know how usually you want to be like wide open, have your eyes wide open? Well, in this case, you don't. You want to look at a joint. At joint H, there are 2 collinear, 1 non-collinear, and there's no load at H, so BH is 0. I'm glad we're doing this.
But, okay.
Doesn't matter.
Okay.
That load coming down on B, who takes the load, the vertical load on B? AB and BG.
Yeah.
So you just,
Did everybody get that? Is everybody comfortable with H being rule 2?
Yes.
Is everybody comfortable with F being rule 2?
yes.
Yeah. So BH and DF are 0, correct?
I
Yes.
just had a question. Why did you say that they put those in anyway? What's the reasoning for having those?
They do take a load, but it's very small.
Oh, it's just super small.
So is CG also 0?
Okay, wait. So now, no. So now look for Sarah, or actually,
I know.
okay. So now look for another rule 2. So Sarah, you want to take a guess?
DG.
Okay. Which joint are you looking at? Okay, look. When you look at joint D, there are 4 members coming in, right? But you just deemed that this one is 0. So now, does rule 2 apply? Yes, and what's 0?
GC and DE.
Just DG is 0. It's the one that's non-collinear that's 0.
Oh.
Right? Okay, let's do another one. Okay, Lonnie, give me a rule 2 here. Right, thank you for giving me the joint. And now what's 0? Which member is 0? FD is 0. Is there another joint that's rule 2? Which joint?
D.
The joint D, and what's 0? DG is 0. Is there another joint? H and BH is 0. Everybody got it?
Yeah.
So be careful. Once you deem a member 0, it's as if that member isn't there, and that another joint can be a joint that follows rule 2. Everybody good with that?
Yes.
Yeah.
So, the external load at B does not matter, it's just if there was an external load at H, then it would not be considered a rule 2.
That's correct.
Okay.
That's why I keep asking you, what joint are you looking at for rule 1 and 2? It's a joint. You have to pick the joint. Once you pick the joint that follows rule 1 or 2, then you pick which one's 0. Good?
What about in the previous picture?
Which one?
Joint,
This one?
the last one we just did,
Okay.
at the bottom, at G.
Okay, so let's look at G. Originally it had 5 coming in, right?
Mhm.
And this one is 0 now. It still has 4 coming in. So it doesn't follow rule 2.
What about the GC member?
GC is not 0.
Okay.
Why would you think GC, which joint are you analyzing to think?
G.
G. Well, the only way rule 2 works is if you have 2 collinear and 1 non. At joint G, there are 2 collinear, but there's 2 non-collinear.
Okay, so it doesn't apply if there's multiple nonlinear?
Correct.
Okay.
It only applies here in rule 1, there are only 2 members coming into that joint. Here, there are only 3 members coming into the joint. The only reason that D works is because one of those members is 0. Even though it's 4, one of them is 0 now. So now you only have 3 members, because you could just pull that guy out. Good?
So what if there wasn't that external load on a joint B? Would that make a DG 0 and
Correct.
then GC would be 0 also?
Okay, so, if, okay, let's get another sheet. If you came in late, come on up and get the sheet. So So what you're saying is if this was not here,
No, on the other picture,
this one?
yeah,
Okay. Okay, so we already know that H follows it, and this is 0. F follows it, this is 0. D follows it, this is 0. Now, if B has no external load, what's 0 now?
BG,
BG is 0.
and then that would make GC also zero.
And then that would make, yeah. Then G follows the rule, because now there's only 1, 2, 3, it would make this 0.
It'd be scary, honestly.
And then it's, yeah.
So then there would be a trust.
There'd just be one thing across.
Okay, so everybody's good with that? Okay, that was the piece I wanted to make sure everybody was good with. So now, so friction we talked about, trust, I want to make sure that you're comfortable with 0 force members, frames you've seen so much, shear and bending moment diagrams, I think you're pretty comfortable with those. When is, that homework wasn't due today, right? It's due Thursday, the day of the test.
I had a question about that one.
Yeah,
So the last one, I think it was, there was, it was
I will not give you a triangular distributed load on the exam. Okay? Because then we're talking about a third order, right? So can I take this? So on this particular case, lights. Okay, so we had a triangular distributed load and then up going down, and it looks like we had a vertical distributed load going up. So with the triangular distributed load, are those two cheat sheets helping you? Yeah?
yeah. But that cheat sheet said the third order.
Yeah, so let me, okay, so if we have a triangular distributed load, and the one on this problem looks like number 4, right? So we have a parabola going down, because you're integrating, the force is going down, it's a distributed load going down. It's gonna be going this way. And then the next one, once you have a parabola going down, we're looking at a parabola going down, you're gonna wind up having a third order parabola going up. So what's your question?
How you knew that it would go kind of start out instead of going straight up, it went out like that.
Probably because it's a combination of two, so let's go back to the Elmo. This is a pretty, a hardish problem, because we're looking at both a triangular distributed load and a rectangular distributed load. So the triangular one, what was it? It was going up.
Yeah.
So if we just, can I write on here? If we just had a triangle going down, what would we have here? We just looked at the sheet.
Yeah, it would just be a parabola.
Going down. Okay, so we would have to have a parabola going down like this, right? And then that's for the shear. And then for the moment diagram, you guys could do this, all this integration stuff. You would have this. Oops. This, right?
Can't see it.
Oh, then you would have this. But now what's also happening is you have this kind of distributed load too. So it's a sum total of both. So a distributed load, this is going up, so you're supposed to have an up slope, not a down slope, right? You do this. I didn't put the forces on the edges. And then from here, you have a positive area, positive slope. Positive area. No, go back. Oh, because I didn't do the distributed load, negative area, negative slope. Positive area. what you're doing is you're summing these two together to get this weird shape.
Okay, so you're like super.
But we're not gonna do a problem like that. I'm already telling you, I'm not gonna give you a triangular distributed load, and then I certainly wouldn't give you a triangular and a rectangular distributed load together. So I'd rather not spend the time in class doing it. Okay. Okay, so what I'd like to do now is, so for the center of mass and center of gravity, I want to highlight some things that Karen did with you, and that you saw on the video. And I know that I did it on the video. I'm not sure if Karen would have highlighted this or not, so I just want to make sure that I am highlighting it. You all, I'm going to zoom in. So first you dealt with center of mass, center of gravity, and centroid, right? Center of mass, center of gravity, center of centroid. So what's the difference between center of mass and center of gravity and centroids? What are they basing the center location on? Okay, so centroids is based on, if it's a 2D centroid, it's based on area. If it's a 3D centroid, it's based on volume. So what is centroid based on? Geometry of something. It's geometry. The difference is center of mass is based on mass, and center of gravity is based on weight. Okay, now, in the world that we live and how we idealize things, all those locations are going to be the same, because we always approximate everything to be homogeneous. And then we attach a safety factor. So the center of mass and the center of gravity and the centroids are really all in the same place if we do that, if we simplify things. But you have to remember that centroids has to do with geometry. And if you're dealing with 2D, it has to do the critical component, and that's the verb that I used, not verb, that's a noun. That's the noun I used in the video. The critical component of a 2D centroid is the area. We're looking at the area. The critical component of a 3D centroid is volume. The critical component of the center of mass is mass. Critical component of the center of weight is weight. Sorry, center of gravity is weight. So I don't know if you took a close look at this in the packet. It doesn't matter because we're going to look at it now. So if we're looking at center of mass, and we're looking at it as 3D, we know the critical component is mass, right? So what do? We sum up all is that centroid? Is centroid the right word here? No, center of mass. Down here, this would be the centroid, because I'm dealing with area. But I'm dealing with mass. So if I multiply the center of mass times the mass of each object and then divide by the total mass, I can find the center of mass of everything. And for an example, and I know I used this example in the video, if I wanted to find where the center of gravity of you guys are in 2D, let's say this is the x-axis, how would I find the center of gravity of all of you? I would multiply Santiago's weight times the distance to me. Lonnie's weight times the distance to me. Sarah's weight times the distance to me. Go all the way down. And then here, DJ's weight times the distance from me. Terrellyn's weight times the distance to me. Right? And I multiply all those together and I would divide by the total weight and I would get some x distance that's the center of gravity of all you guys. And then I can do the same thing this way. I could say y bar times Santiago's weight, y bar times Lonnie's weight, y bar times Terrellyn's weight, y bar times Maria's weight, and do all you guys and then divide by the total weight, and I get the y bar to all of you. Makes sense, right? Right? Okay. And what you guys are, as a class, we are a composite of each one of you. A composite is a mixture, right? There are 34 of you in here. Right? So we're taking all 34 of you that have your own weight and multiplying it by the distance to you to determine the location of where the center of gravity is for you. Makes sense, right? That's the same thing that we're doing here. We're finding the distance to the first weight, distance to the first mass, plus the distance to the next mass, distance to the next mass, distance to the next mass, taking them all together and then divided by the total mass, and what do I get? I get the center of mass in the x direction. Everybody's comfortable with that? Put your hand up. Everybody's comfortable? Okay. This thing right here is called the first moment. How many of you watched the video on centroids? Okay, how many watched a video on the center of the moment of inertia stuff? Okay, so does this make sense that this is a moment? If I sum up the distances to the forces and multiply a distance by a force, is that a moment? Yeah, that is the definition of a moment. You take a distance, you take a force, and you multiply it by a distance. That is a true moment, right? It causes a rotation. Well, that word, they've been giving that word moment a little bit of leeway. Now, if you multiply the distance times the mass, that's a moment too. If you take the distance times the area, that's a moment. And if you take the distance times the volume, this is a moment. And all these things are called the first moment. Okay, so this is the technical language that I just want you to know, why something. So the moment of inertia is really the second moment. The first moment is you take the distance and multiply it by the critical component, whether it's volume or area or mass or weight. That's the first moment. And notice in the last column, here it is. It's called moments. And I have it written in integration too, but we're not going to do integration. But here, notice this, moment of force, we got that. Moment of mass, moment of mass, moment of mass, moment of area, moment of volume. These are all the first moments. So how do you think we get the second moment? What do we have to do? Multiply it by another distance. So the first moment is taking the critical component and multiplying it by a distance. The second moment is taking this value and multiplying it by another distance. So we have the critical component times two distances. So you'll see the units. Okay? So now, let's look at the reason for doing this. So let's go back. I don't know how to do rotate counterclockwise, so we just have to go in a circle. It must be like an all per shift. Okay, I did it all in integration, but you've done this stuff in integration. We're not going to bother with the integration. The more important thing in engineering is when we design things, this is a composite. It has a cover on the back. It has a piece here, a piece here. There's a bunch of buttons. This is a composite. If I wanted to find the center of mass or the center of weight or the centroid of volume of this, I have to worry about every single little thing on here. And that's what we're doing in engineering. I can integrate each one of these things, but in the end, I'm trying to find the whole thing of all of them. So that's the focus. So I did some integration here, but you can just ignore it. What I did give you up here, again, if you came in late, we're going to be looking at this sheet, back and forth. Okay, so make sure you have this one, and we'll come back to it in a little bit. So let's look at what is moment of inertia used for, because that's always what I want to know. Why am I learning something? So, moment of inertia is used, and that term, I have to say, the moment of inertia is equal to the second moment of, do you know? Take a guess. Which one? Area, volume, mass. And that you probably figured out from physics. Because remember, didn't they do physics demos with moment of inertia? They were spinning things, and depending on how far the mass is away. So if I have a rope with a ball on it, and the rope is a foot long, and then I put a 2-foot rope on it, which one has a higher moment of inertia? The 2-foot long. Why? The distance is longer. We learned that you take the first moment, you multiply it by a distance. So the bigger the distance, the bigger the moment of inertia. So moment of inertia is really the second moment of mass. Then there's the second moment of area. These are the guys, these two, not weight, not volume. These are the two critical components that are used in moment of inertia. You got Rachel and Sarah, did you? I want you to be able to hear what I'm saying, so
I got stuck on something,
No,
but
sure,
I can
tell
ask
me.
you later. It was just the integral of these.
Oh yeah, let's do that later.
Yeah.
Let's do that later. Okay, so moment of inertia is the second moment of mass. So we're talking about mass. This term inertia has to do with mass. The other second moment that we deal with is area. We don't do volume, and we don't do weight. So it's only these two. But it's become fine to call this moment of inertia too. Even though moment of inertia really only has to do with mass, it's been accepted in industry that moment of inertia is also based on area. Okay, they use the same terms. What variable is used to describe moment of inertia?
I?
I. Was that in physics too? Good. Capital I, moment of inertia. So here are three uses in engineering that you need moment of inertia. Two of them are civil engineering examples, like static examples, and one is a dynamic example, which could be mechanical or aero. So the first one is beam design. And you're going to see all this in the next. What are the two first courses you're going to take when you transfer, if you're a mechanical or civil? Dynamics and you probably will, but that's not based on anything. Well, I guess it's based a little on physics. Of course it's based on physics. But based on engineering classes. Mechanics of materials. And it's either called mechanics of materials or strength of materials. And mechanics of materials or strength of materials, whichever, it's the same course, it's just called different in different schools. The first thing they're going to do is they're going to do a little bit of statics problems. The next thing they're going to do is shear and bending moment diagrams, and you guys are going to be whizzes at them. Sit in the front of the room, show off. Then they're going to look a little bit, then you're going to start doing things like this. You want to connect this thing to this thing, how many weld joints do you need, or how many bolts do you need, because it's based on stress, which you learn in materials, and it's based on some of the forces in the X and some of the forces in the Y. So statics and materials are the two prerequisites for the two first classes you're taking when you transfer, dynamics and strength of materials. And then they're going to have you take thermal and fluids, and you go to San Jose State Engineering 100W, which is a writing class. Anyway, so you're going to see a lot of this in strength of materials. So what are we looking at here? The idea is the maximum stress. So here is a beam that is being loaded on top and is causing it to bend. It's simply supported. Oh, I want to show you something. Yeah, I'll show you some ugly things.
Wonderful.
Look at my finger.
Ew.
It got smashed playing kickball. I caught the ball though.
Like recently?
Recently, a couple weeks ago. So, the key is that the muscle, the tendon here got separated from the muscle. So if I don't do anything, I'm going to have a forever finger that looks like this. And this is better than it used to look. Look at this cool design.
Did you 3D print that?
Look at it. I did not, but we certainly can, and I should. This is probably a half-cent part. They charge $12 for it. Biomedical engineering at its best. What is it? It's simply supported. Look what they're doing. It's applying a load here and here, upwards, and a load here downwards to force my finger to go like this, and for the tendon to reattach itself to the muscle. Now, when I bought it, my finger was a little swollen, so now what I do is I put a paper clip in it.
That's engineering out of
So my finger, hopefully the tendon will grow back to the thing. But isn't that simply supported, right? Isn't that
Something is up.
okay.